So if I do number 4, this is in section 3.1, I'm taking the derivative. So I'm going to take e to the 5th, take its derivative. Well, the derivative e to the 5th is just 0 because e to the 5th is a constant. So now I look at number 6, and if my function is 7/4 x squared minus 3x plus 12, you ask me to take the derivative. I'm going to draw a line and say, okay, I'm taking the derivative. So you pull out the constant times the derivative of x squared is 2x, minus pull out the constant, and the derivative of x is 1, and then the derivative of 12 is 0. So this is going to be cancel out a common factor of 2. It's going to be 7/2 x minus 3 is the derivative. Then we go on to 14. 14 is y is equal to x to the 5/3 minus x to the 2/3. So I draw a line and say my derivative is pull down the constant, boop, boop, pull down the constant, then the derivative would be, pull down the constant and then x to the subtract 1, and you get 2/3 minus pull down the constant, subtract 1, and it's negative 1/3. So if we wrote that without negative exponents, it would be minus 2 over 3x to the 1/3. And that would be your derivative. So that's 14. Let's look at 18. So for 18, it's y is equal to the cube root of x, 2 plus x. Well, the first thing we notice is that's the same as x to the 1/3. And so I have two things multiplied together. I do not have a rule that allows me to deal with things multiplied together. So I change the form. So change the form by distributing first. So I get 2x to the 1/3 plus x to the 4/3. Right? Because x to the 1/3 times x to the 1 is the same as x to the 3/3. And you add the exponents when you have like bases and you're multiplying. So that's my function. Now I draw a line and say, now I realize I've changed the form, and now you can take the derivative. So the derivative is 2, so I'm going to pull out the constant 2, and then the derivative of x to the 1/3 is 1/3 x to the negative 2/3. And the derivative of x to the 4/3 is 4/3 x to the 1/3 when I subtract 1. So that's going to end up giving you 2 over 3x to the 2/3 plus 4/3 x to the 1/3. Right? So that's 18. 30. Now we're jumping down to 30. So notice we had to change the form before we actually took the derivative. That's something we're going to see a lot. So here, if I have this t squared over 4t to the 3rd, the first thing I'm going to do is notice that 4t to the 3rd, over here in my scratch, is just 4 to the 3rd times t to the 3rd, or 64t to the 3rd. So over 64t to the 3rd. So when I look at this, I see a plus b over c. So a over c plus b over c is a very powerful way of looking at a fraction and breaking it up into two smaller fractions. So I can break this up into 1 over 64t cubed and 16t squared over 64t cubed, and then add them together. So that's going to be 1 over 64t to the negative 3rd plus, I'm going to cancel those out. That's going to leave a 4t on the bottom. So that's really 164t to the negative 3rd plus t to the negative 1st over 4. All I've done so far is change the form. I draw a line so that the reader knows now I'm going to take the derivative. So the derivative is this negative 3t to the negative 4 minus 1/4 t to the negative second. So to remove negative exponents, I'm going to put that t to the 4th on the bottom. And here I'm going to put that t squared on the bottom, and that would be your derivative. So now if I look at 32, so for 32 I have y is equal to e to the x plus 1 plus 1. So I've got to change the form because this is not e to the x. So I know that if you have x to the n plus m, you can break it apart in x to the n times x to the m. So usually we go this way, but again, in calculus, we often like to break things down into pieces. So this is a tool, this multiplying like basis, that is helpful. So this is really e to the x times e plus 1, and now you're ready to take the derivative. So y prime is just, well, first I'm going to pull out this constant e, and then times the derivative e to the x is just e to the x, and the derivative of plus 1 is just 0. So now I can add the exponents because I have like bases, and I have e to the x plus 1. So that turns out to be its derivative. Then when you look at 48, which is the bottom of my page over here, so for 48 it says find the first, second, and third, or I'm sorry, first and second derivatives. So if these derivatives, derivative of e to the x minus x cubed is 3x squared, and then for 3x squared it's going to be 6x. So there's the first, second, and third derivative. And if we go over to our old buddy Desmos and plug them all in, it looks like that where I have a peak here, it looks like I have a 0 here. So those derivatives match up, yes? And then it looks like where I have a 0 here, so let's see, that's the first derivative, is that one. And then, let's see, then the derivative of this, where it has a peak, this one has a 0. So yes, it matches up perfectly. Yes, so we're trying to make peaks and valleys and zeros match up to see if one function is the derivative of the other. So that's 48. Then I'm going to go to 52. So what does 52 say? 52 says that I've got S of A 0.882a raised to the 0.842. And it says that this is the number of tree species, S, in an area A in Malaysia has been modeled by this power function, where A is measured in square meters. So it says it wants to find the derivative of 100 and interpret our answer. Well, first, the derivative, just to be clear, note, is equal to the change in S over the change in A. So this is going to be change in species number divided by change in area, right? And so those units are going to be a number of species divided by square meters. So it's going to be, our derivative will give us an answer in the number of species per square meter. So let's first take our derivative. And so if I take my derivative, I get 0.882 times 0.842, 8.842 minus 1. So that's going to give us, if I take 0.882 times 0.842, I end up getting 0.742644 a to the, and if I take this minus 1, I'm going to get what should be pretty easy to see, I get a to the negative 0.158. That's my derivative. And so S of 100 is just going to be 0.742644 a raised to the, oh, don't forget this is this many. Oh, okay. This is going to be 100 raised to the negative 0.158. So let's take 0.742644 times 100 raised to the, in parentheses, negative 0.158, and we get raised to the, this is 100, this should be raised to the, what's up, 0.742644 times 100 raised to the negative 0.158. So we get approximately 0.36, which means at this exact instant that we have 100 different species, the change in species per square meter is about a third of a new species per square meter, right? So in other words, for every 3 square meters, we're getting a new species every 3 square meters at the instant when we have 100 species. Okay, so that's 52. Let me do 56. While people are coming in, hopefully they won't be too horrible. 56 is when does something have a horizontal tangent line? So I've got e to the x minus 2x. It wants to know when does it have a horizontal tangent line. Well, I take the derivative and get this, and horizontal tangent implies the derivative is equal to 0. So I set my derivative equal to 0. Shh, as you come in, be quiet for just a second because I'm finishing up your homework video. And so then if you get this, you just take the natural log of both sides to solve it. So you get x is equal to the natural log of 2. So that's where the horizontal line is, the tangent line is horizontal, because that's where we have a derivative of 0. Shh, if you want a good homework video, again, try and whisper to your friends. We're almost done. 58. Find an equation of the tangent line to this curve. Okay, so I want to know when this curve is parallel to this curve. So what I'm going to do first is get it in a form I like, which is 32x minus 15. So first I want to know where they're parallel. So I find the slope of this one to be 4x cubed. That's my slope machine for that curve. And for this one, I find the slope machine of this one to be 32. And so I'm wanting to know when is this equal to this. So if you divide, you get 8 is equal to x cubed. So in other words, x is equal to 2. So 2 is where they have the same slope, which means they're parallel. So I want to find the equation of the tangent line to this curve at 2. And so I want to do y is equal to x to the 4th plus 1 at x is equal to 2. So to find the equation of the tangent line, I do this. And so this is going to be my x1. My y1 is just going to be f of 2. So it's going to be 2 to the 4th plus 1, which is 4 times 4, which is 16 plus 1 is 17. So this is almost my tangent line. So to find m, I take my derivative. And I get 4x cubed. So if I do the derivative at 2, I get 32. And so the equation of the tangent line is y minus 17, 32x minus 2. That's the tangent line to this curve when it is parallel to this curve. Great work. Bye.